Here we're supposed to find the average rate of change of the function f of x equals x squared plus 1 on several intervals that you see given down here. We are also supposed to draw the corresponding secant lines on the graph provided here to the right. So the first thing you're going to want to recognize is that with interval notation, although they look like coordinates of a point, these are actually the two x values over the interval in question. So for example, the first number in each of these intervals is really x sub 1, the first x value, and then the second number in each of these intervals is actually the second x value. So for example, we're asked to find the average rate of change, or the slope, between the points whose x values are -2 and 3. So when you see these two numbers, it's important that you realize that they are the x values of the points in question, and then we can use either the equation or the graph to find the corresponding y values of the points, and then we will proceed to find the slope between those 2 points, because by definition, the slope of a secant line can be found by just finding the slope between 2 points on the line, and that gives us the average rate of change of the function over that given interval. So for example, if we didn't have a graph, we could take the equation f of x equals x squared plus 1, and we could simply replace x with -2, simplify that to see that that is 5. That would be the y value of the function when x is -2. Then we could repeat the process with the second x value given, which was x equals 3. And if you replaced x with 3 here and here, you'd get that f of 3 is 10. Now to find the average rate of change, we simply need to find the slope between those 2 points. I also want to show that because we do have a graph, that we could have estimated those values by using the graph. So eventually we need to draw a secant line that goes through the points whose x values are -2 and 3. So if you look over at the graph, when x is -2, you can simply go up to the point on the graph to see that the y value would be 5. Then to get the second point, had we not used the equation but used the graph instead, you would go over to the second x value of 3, move up to the graph, and find that that point on the graph has a y value of 10. Now I need to draw the secant line that passes through those 2 points. So I will go to -2, 5, and that will be one of my points on my line. And then as a second point, I need to make sure my line passes through 3, 10. And I am trying to color code this, so you see that the interval I colored red, and I'm drawing the secant line in red. So now we have 2 different ways we can find the slope. Using arithmetic, we can just use the slope formula that basically says take y2, which is 10, subtract y1, which is 5, and then divide that by x2, which is 3, and then subtract the first x value, which happens to be a -2. Simplifying that, you would get 5 in the numerator, and then you'd get 5 in the denominator, and you'd find out that the average rate of change over that first interval is 1. I'm using m to represent the slope, or the average rate of change. Notice you could estimate the slope using the graph of the secant line by saying to get from this point on the graph to this point, you would have to rise 1, 2, 3, 4, 5 units, and that's why we got the 5 in the numerator. That would be the rise. And then the run would be how far you move to the right, which is 1, 2, 3, 4, 5 units to the right, and we typically call that the run. So the rise is 5 and the run is 5, giving me a slope of 5 divided by 5, or 1. Now later in the video, what's going to become really important is what the run is. So you might notice that since we wanted to find the average of change between -2 and my second x value, x sub 2, was 3, that those 2 numbers differ by 5 units. Later in math, we typically call that horizontal distance between those 2 points, the run and the slope, h. So for this example, the horizontal distance between -2 and 3 is 5 units, which just means to get from the first point to the second point, you have to run 5 units to the right. So later in the video, you'll see me saying that for this interval, the h value is 5. Right now, that won't make any sense. But when we get down to part f here, which has that h, it's nice to know what that h represents. So let's just remember that in our first interval, when the distance between our 2 x values was 5, that the average or change, or the slope, came out to be 1. And we move on to part b. To mix things up, I'll draw the secant line for this interval first, But again, remember that the two numbers in interval notation are both input values, so we're actually saying find the average rate of change between x equals -2 and x equals 2. So on the graph, I notice once again that when x is -2, y is 5, and that won't change on any of our examples. You'll notice that x equals -2 is the first number in the interval in all of our problems. So I need not repeat that process of finding that first y value. So now that we changed the second x value to 2, you notice we get a y value of 5 this time. And when I draw the secant line through those 2 points, it'll be obvious what the rate of change is. So at -2, 5, that's one of my points on my line. And then I have to make sure that my line also passes through 2, 5, which I think I've done that. So visually you notice that my line is horizontal, and we know that horizontal lines have a slope of 0. There is no change. Now, actuality, the graph actually goes down and then back up. But on average, you end up the same place as where you started. You started with a y value of 5, you ended with a y value of 5, so there should be 0 change, so the average change should be 0. And if you did the arithmetic on this example, when you go to do y2 minus y1, in the slope formula, you'd get 5 subtract 5, and in the denominator of the slope, x sub 2 minus x sub 1 would come out 2 subtract -2, and this makes my numerator 0. My denominator happens to be 4, but that doesn't matter because 0 divided by just about any number comes out to be 0. So it's important to remember that I skipped using the equation here. In this particular example, I could have gotten the second y value by replacing my second x value of 2 into this equation. The reason I could skip that is because we have a graph. So let me clear this and summarize what we found. We found that over this interval, the slope came out to be 0, whereas the first example it came out to be 1. And I will summarize that, but I also want to, in my summary, record what the horizontal distance is between -2 and 2. So for example, if I was looking at the rise over the run, the rise from this point to this point would be 0. You don't have to go up or down at all to get from here to there. But the run would be how far you need to move right or left. And I would have to move 1, 2, 3, 4 units to the right. Simply put, we chose an interval between -2 and 2, and that horizontal distance between those 2 points is 4. So in my summary, I'm going to write that when we picked an interval of length 4, there's 4 units of length between these two x values, the slope came out to be 0. In the next example, we are to find the average rate of change, or the slope, between 2 points whose x values are -2 and 1. So once again, remembering that those are both x values of points on the graph. To find the y values, again, you can use the equation given, or you can use the graph. The graph is much faster, but graphs are more inaccurate than equations. So remember, you could plug -2 into the x value of this equation, but we've done that earlier in the video. We got 5. It's the second x value that's new. In fact, mentally, you probably could replace x with 1 in this equation and get 1 squared plus 1, which would be 1 plus 1, or 2. Or you could simply look at the graph and look over at x equals 1 and go up and see that that point would have a y value of 2 here. However you do it, you get those two y values to be 5 and 2, whether you use the equation or the graph. If you calculate the slope quickly, y2 minus y1 over x2 minus x1, you would see that you get -3 in the numerator and +3 in the denominator, meaning the slope would be -1. You could also get that quite accurately in this example if you drew the secant line. So my first point, as always, is -2, 5. My second point in this example was 1, 2, so that would be right here. And if I wanted to estimate the slope of the secant line, now remember it would be just an estimate since you're on a graph, but for this example it comes out pretty nice. To get from this point, -2, 5, to the point 1, 2, which is this one, I would have to go down, which would be considered a negative rise. In fact, I have to go down 3 units, and that's why we had a -3 in our numerator. The rise is -3. The run would be how far you need to move to the right. It's actually also the h value in this problem. I would have to move 1, 2, 3 units to the right. So that's why we got a run of 3 in the denominator, which I'm calling h in this example. Since our interval was from -2 to 1 on the x-axis, those two numbers differ by 3 units. So let me summarize this. So here we found when we shrunk our interval to a distance of 3 units that the slope came out to be -1. So moving right along, the next interval has us finding the slope between x equals -2 and x equals 0. This is always the point -2, 5. If you were to plug in x equals 0 into the equation here, you'd get 0 squared plus 1, which is just 1. Or you get that same information by just looking at the graph and saying when x is 0, the y value is 1 right here. The slope, if you did the arithmetic, comes out to be 1 subtract 5 is -4. And 0 subtracting a -2 is the same as 0 plus 2, so that comes out to be 2. And simplifying, you get that the slope is -2. Let's draw the secant line between the point -2, 5 and 0, 1. So just making sure my secant line goes through the point 0, 1 there, and also passes through the point -2, 5. So had we not done the arithmetic, you could have looked at this is your first point, this is your second point, and said that the rise would be negative because you're going down to get from this point to that point. You'd be going down 1, 2, 3, 4. So the rise was -4. And this time the run, which I'm calling h in this example, is 2 units. So the rise is -4, and the run, or the h value for this interval, is 2. So let me summarize that. When our interval is 2 units in length, the slope came out to be -2. And I can put that in the graph as well. The slope is -2. I forgot to label that the slope of the purple graph was -1. Our last specific interval has us going from that point that has stayed fixed in this whole example, where x is -2 and y is 5, but we're changing the second x value to -1. And it's pretty quick to get the y value using either method, either using the equation or the graph. If you replace x with -1 in the equation, you would get that the y value is 1 plus 1, or 2. You could also quickly get that information on the graph by moving over to -1 in the x direction, and then up until you hit the curve, which has the point here with a y value of 2. If you want to find the slope using arithmetic, that's quite easy. That would come out to be 2 subtract 5 is -3, and x2 minus x of 1 would be -1 plus 2, and that simplifies down to be -3 over 1, which is -3. So I'm going to erase the division by 1 because that's not necessary. So let me draw the secant line there and verify that I can get that graphically as well. Always starting at the point -2, 5. And this time I need to make sure my second point on my secant line goes through the point -1, 2. So that's about right there. It's not perfect, but it will do. And if I were estimating the slope of the secant line using the graph, I would say we need to get from this point to this point by going down 1, 2, 3 units. So my rise would be -3, which we got before. And the run would just be 1 unit. And that's why we got a 1 in the denominator. I erased it, but it was a 1 there. And remember that it's this run that we're calling the h value. So if our interval is only 1 unit wide, right, from -2 to -1 is only a 1 unit difference here, we get the slope is -3. So let me summarize that. We picked an interval whose length is 1, and we got the slope to be -3. Now, in mathematics, whenever you do the same thing over and over and over, with only one thing varying, in fact, in this example, the only thing that varied in this problem was our second x value. It went from 3 to 2 to 1 to 0 to -1. Everything else in the problem stayed the same. So what part F is trying to accomplish is to do the problem one time only and find a quick method to go from the question to the answer in all 5 parts. Hopefully you realize that although doing part F is tedious, once done, it makes the first 5 parts here go very quickly. So doing the problem much the same way, thinking of these numbers in the interval notation as 2 x values, x of 1 and x of 2, that means that my first x value is -2, and we've learned over and over that that gives you a y value of 5. You could use the equation for that, which by the way was x squared plus 1. Simply replacing x with -2 would give you a y value of 5. It's this second x value that's a little different than normal. It's not an actual specified number. It says my second x value can be found by taking -2 and moving to the right a little bit, assuming h is positive, And h would just represent how far you move to the right. So for example, in our problems we did before, you can pick one, like the one in red here, and notice that when h is 5, my second x value would be -2 plus 5, and that simplifies down to be the number 3, which it was. If you go up, when h was 5, our second x value was 3 here. And that argument can be made for all the different parts. Changing the h value changes your second x value. The difficulty in this problem is the algebra that comes out, because to get the y value, we can't use the graph, but we can use the equation. So to get the second y value in my second point, I could replace the input with -2 plus h. And of course, if I replace this x with -2 plus h, I need to replace this x with -2 plus h, and remember to put parentheses. So if you remember, this is a way you could always have found the y value of the function just by plugging in the x value in question. It just turns out that my input is now an algebraic expression, -2 plus h. So here I am replacing x with literally parentheses -2 plus h and copying the squared and the plus 1. I'm going to simplify this and put that right here as my second y value. I'm not sure I left enough room. We'll find out. So simplifying this guy, I have -2 plus h squared, which if you want the long way, that means when you square something that you're multiplying the base by itself, and don't forget to copy the plus 1 at the end. And if I FOIL, or I like to say distribute both the terms, I would get 4. Distributing this term here, I'd get a -2h. And then I've yet to distribute the second term of h here. This times this would give you a -2h. And this times this gives us h squared. And don't forget again to copy the plus 1. I'll simplify this and put it in descending order. We get h squared. -2h and -2h are like terms. They combine to give -4h. And then of course 4 plus 1 is 5. So this is my second y value. And as I said before, I didn't leave enough room to actually copy it in there. I could shrink it down a bit. It would be more difficult to see, but then it would fit. So if you want to summarize the process thus far, they gave me a problem with two x values, -2 and -2 plus h. You could take those two x values and plug it into the equation given to find the corresponding y values. Plugging in x equals -2 gives you a y value of 5. And plugging in an x value of -2 plus h, after simplification, gave us h squared minus 4h plus 5 here. So let me erase all of these markings because it's getting very busy. So we plugged in our two x values and we got our two y values, and this time it just happens to include an algebraic expression rather than a number. But we can still find the average rate of change over this interval, which I denote as m, or the slope, by doing y2 minus y1 over x2 minus x1. And again, I'm using m to represent the slope. So my y sub 2 was h squared minus 4h plus 5. Subtracting y sub 1, that would be subtract 5. So it's important to know all of this is my y sub 2, and I'm subtracting y sub 1 here. Then in the formula for slope, we divide by x sub 2, that's this guy, subtract x sub 1, which happens to be -2. So I'll put that in parentheses. Now we need to simplify this down. I get h squared minus 4h. 5 minus 5 is 0, so I need not write that. And in the denominator we have -2, and this is technically a plus 2 because when you subtract a negative it becomes plus. And -2 plus 2 is 0, so I need not write that. It's basically h plus 0, or just h. And since all three terms, 1, 2, 3, have a factor of h in them, I can simplify further. Now remember, you cannot cancel terms, you can only cancel factors. So for example, because this is a subtract symbol there, that makes this a term and that a term. And those being terms, you are not allowed to cancel any part of them. So a common mistake every teacher has seen in the world is to try to cancel this h with this h, or that h with that h, and it just simply cannot be done because of that subtraction there, making those two things terms. What I'm going to do, since h is a factor in both of those two terms, I'm going to factor it out. This is one method of doing it. So if I factor out an h, I'd have to ask myself, what would I have to multiply h by to get h squared? It's like you're doing the distributive property backwards. When someone distributes this, you'd need an h here so that they would get h times h, or h squared. And then I would have to put a negative 4 here so that when someone distributes the h to that, they would get negative 4h. And I'm going to copy my denominator of h here. So now I always like to point this out because it's very important, because there's so many common mistakes that go with this, that this whole thing as a unit is a factor. And that's because that entire thing is being multiplied by h. And things separated by multiplication or division are factors. So I have 3 factors. This is a factor, that's a factor, and h minus 4 is a factor. So I can cancel any of those 3 if I have anything common in the numerator and denominator, and I do. I have a factor of h on top and a factor of h on the bottom. Those can cancel legally, if you will. But what is not legal, that I'd like to point out, is to cancel this h with that h, and that's because within the parentheses, this h is a term. It's being separated by the 4 with a subtract. And also, if it was addition, same story, these two things would be terms. And you are not supposed to cancel terms in math, only factors. So I will do that. If I cancel this factor with that factor, I'm left with the fact that might have been obvious from the very beginning. I bit my tongue the whole video because it was becoming more and more obvious that there's a simple way to find the slope over an interval. And that's just to take the length of the interval, which I've been calling h throughout the video, and subtracting 4. Think about that, how cool that is. So it was a lot of work to find the answer to part f. I guess I should summarize that if you have a interval of width h, that the slope comes out to be just simply h minus 4. Meaning in all of these problems, we could have skipped everything we did, and we could have just did part f first. Imagine we had done no work on a through e, and we just did part f, and we found out the relationship that the average rate of change over an interval can be found by taking the run of the slope, the length of the interval, and just subtracting 4. So for example, in this first part, you could notice that the numbers negative 2 and 3, here they are on the real number line, differ by 5 units. The run is 5. So the slope would come out to be 5 minus 4, or 1, which it did. The slope is 1. And you could repeat this process for every single problem, and it would be very, very quick to do so. Rather than plugging in the 2x values to get the y values and calculating slope, you simply could have said, look, negative 2 and 2, those two numbers differ by 4 units. You can see it. And if h is 4, my slope would be 4 minus 4, or 0, and that's exactly what we got there. We got a slope of 0. And you can see here that 3 subtract 4 is negative 1, and that 2 subtract 4 is negative 2, and finally that 1 subtract 4 is negative 3. I could have done these 5 problems in about 5 seconds after doing part f. So the power of part f really relies on how many of these steps are you wanting to do. If you're wanting to do many of them, like 5, it's probably better off to do the problem once, like we did in part f, and just recognize the pattern. Now the real reason for doing part f really comes later in calculus, but that's a story for another video. So as always, I hope this all made sense, and best of luck.